Let's finish the week by looking at two problems that we can solve with the Navier-Stokes equation. The first one, planar Couette flow, I'm going to show you an exact solution, and the second one, which is a Stokes law solution, I'm going to outline how to find the solution. Couette flow is a very special solution. It's a problem which is highly symmetric, and despite its idealizations actually has many areas of applicability. We're going to assume we have two solid flat plates which extend infinitely, and that between these flat plates there is a fluid. The lower plate, I'm going to draw in black here, and it's stationary. The upper plate, I'm drawing in blue here, it's moving. And it's moving at a speed capital U, let's say in the x direction. And that means that the fluid in between the two plates here, which is separated by a distance h, will have some velocity profile u of z, which I've shown schematically. Remember, these plates are infinite, so we're going to assume that u does not depend on x at all. We're also going to assume that flow is steady, that it's two-dimensional, and that the fluid is incompressible. So before we get into the solution, remember we have to look at boundary conditions. And the boundary conditions for this flow are effectively no-slip conditions, which means that if you go right adjacent to the plates, then the fluid is moving the same velocity as the plates. In other words, u of 0 is equal to 0 because the lower plate is stationary, and u at z equals h is equal to capital U. Then we have our Navier-Stokes equation, and just for simplicity I'll write it down here in 2 dimensions. Remember, we've said that u is only a function of z, that is, it doesn't depend on x or time, and that means that du dt is 0, it means that du dx is 0, and since there's no w, then the w du dz term is also 0, meaning that the left-hand side is 0. We're going to retain the pressure gradient just for a moment, but in the viscous term here we can eliminate d squared u dx squared. Now remember, this is an infinite domain, so if we go infinitely far in the x direction and there's a pressure gradient everywhere there, then we're going to have infinitely positive or negative pressure. That means that the flow can't sustain a pressure gradient. In other words, dp dx is 0. So this might actually seem a little bit unreasonable to you, but let's imagine that instead of these two flows being flat plates, they were some cylindrical plates which were describing, say, a wheel bearing, and that this was the small gap in between those cylindrical plates. Then you could imagine that the infinite solution is realistic. And so we end up with the very simplest equation we can get out of the Navier-Stokes, and that is d squared u dz squared is just 0. In other words, u is linear. If we write u equals az plus b, then we know b has to be 0 because u of 0 is 0, and we know that u of h is equal to u, and that gives us u as a function of z is equal to uz on h. So this is the solution to planar Couette flow, where we have a linear velocity gradient in between the two plates. So our last task of the week is to have a look at another classical viscous flow solution, and this one is Stokes' law. And I'm not going to derive it exactly, but I'm going to show you how to get the answer. So Stokes' law is for small particles which have negligible momentum that are falling through a fluid. Let's draw the particle here, drawn in black. It's going to have a radius r and density rho s. Now viewed in the frame of the particle, the fluid outside the particle is flowing past it following streamlines which look something like these blue lines here, and we're going to assume this fluid has a density of rho w. So the first thing we do is we look for the density difference between the particle and the fluid, and this is going to be written as delta rho, which is rho s minus rho w, and we're going to assume this is greater than 0 so that the particle is falling under its own mass. The forces on this particle include the gravitational force pointing down and a drag force which is acting in the opposite direction. Now it turns out that this drag force is due to two things. It's due to higher pressure beneath the particle than there is above, and it's due to the viscous shear stress on the sides of the particle. And the derivation to show that is actually quite long-winded, so I'm not going to go through it in detail, but if you want to look at it, there's a link down here and you're welcome to go and look at that in your own time. If you don't want to look at that, you can just accept it from me that the drag force can be written as 6 by times the radius times the coefficient of viscosity times the vertical velocity w. Now at terminal velocity the drag will balance the gravitational force, and the gravitational force is just the volume of the sphere times delta rho times g. This is just our mg. What we want out of here is we want to find the vertical velocity, and you can see that's pretty simple. We can equate these two equations and we find that the terminal velocity w goes with r squared and inversely with viscosity. In other words, if you want to make a particle fall very slowly, let's say you want to visualize what's going on in a fluid, then making the particle as small as humanly possible will minimize this settling velocity here. So this is not a complete solution, but it does give you an idea of how viscous shear stress acts on very small scales to retard the fall of particles. And I'd like you to keep in your mind how the action of shear stress amplifies at small scales, because that's going to be a theme that we come back to in next week's lectures.